Okay, hello Simon, how are you? As I promised you kind of presentation or show video about the problem that I solved during this VRES. Okay, so let's start. And I want to share a figure with you. Okay, so I'm gonna explain you through an example. Okay, so the problem that we have, there's a scope of the problem that we were kind of working on. So the first problem, it was to pass from discrete data to functional data. And the example that we were working on and try to understand a little bit what's going on, it was data from 35 different weather stations in Canada. And then we can see in here that we have like 35, like each color represents the data in time of the temperatures in 35 different weather stations in Canada. We can see that the data is a little bit wiggling. It's a little bit noisy. And and there's a lot of data. You have for each weather station, you have 35 data points, and multiply by 35, then you have matrix 35 for 365. So it's a little bit of data. And then if you have different stuff, or if you have like the time frame is a little bit shorter, then, or if you are if you are doing measurements of temperature every hour, then it's going to escalate to big. Instead of 365, you have more data points. So it's increasingly a lot. And then that's a problem for doing any kind of analysis. So there's a technique that it's called functional data. And that's the first part of the problem that I solved. So we got the discrete data, and we want from this wiggling data to, I'm gonna share the other one, to something like, just let me grab the screen, to something like this. So what we have in there is like the same data that we have in a discrete way, and we have this kind of a smooth way of having the data, and all of them become functional data. So I have a function for each of these weather station. So instead of having 365 data points for each weather station, what I have is a function of time that I can access at any, if I want to, that I have right now. So I have a significant reduction of dimension at the moment, because I have I pass from having 365 data points. I pass to have probably 3 or 4 parameters in a function, and then I have the independent variable that is time. And then from 365, I pass to have something like 4 parameters, and that is a significant reduction of dimension that we are experimenting with this solution in for storing data. And the techniques that I use for passing from discrete data to functional data, it was basically not parametric regression. Instead of having a linear regression, which is trying to fit the data points to a straight line, instead you have many different techniques, and I only use 3 of them. One, it's called spline regression. The other one, or natural splines. The other one is radial base splines. And the other one is Fourier transform or trigonometric polynomials. And those were the 3 basic techniques that I used to pass from discrete data to functional data. And then I want to show you the functions that I use. They were, okay, this is the main script where I use the different functions. So the function that I use, RBF, is the radial basis functions to pass from discrete points to radial basis functions. So this is the function that I used that receives 2 vectors of data and a penalization factor, and then basically uses a linear regression or a projection over the column space of the data points, and then gets those beta or those coefficients for the function that I'm going to use. And then I use also this fine RBF, which provides you a vector with a little bit more fine. Instead of having the 365 points, I want to do it like, I don't know, hourly. So I divide it by, I multiply by 24, and then 24 multiplied by 365, then I can have like those data points with T, and then I'm gonna have like impression or a little bit more of a smooth plot. And yes, that was basically the first part of the problem, and I can show you that this is the result that one can get. And we obtain this mean function because right now you're not gonna have like 35 different random variables. Instead, you're going to have like 35 random function variables, and then you can do some statistical analysis for that. Okay, but I didn't share with you the plot that I wanted to show you. This is the one. Okay. And then the second part of the problem that I was solving, it's once you have the functional data, you want to do some you want to obtain the main features of this functional data and what represents the most the functional data, and for doing that, where I use principal component analysis, or FPCA, which is functional principal component analysis. And then what you basically do is you put, or what I did, it was to put everything, all those 35 functional data into a matrix, and I put in a way of all those 35, whether the stringing were the columns of that matrix. And after that, I did principal component analysis by SVD decomposition, singular value decomposition. So I'm going to show you what I did. I'm going to show you the code that I did. And then this is the plot. And then what you have to do is, I told you that I need to compute the mean function. And then this is how I compute the mean function. And then after that, I have to kind of subtract the mean function to all my data, and then I'm gonna have like centralized data, and then I can and then what I'm going to have by the end of the subtraction is gonna be that all my data is standardized or centralized, and then I'm gonna have like all the features that I want to find interesting, and then I'm going to have the PCAs to explain me the main features. And then I can do further analysis with that PCA, or I can do some dimension reduction, a further dimension reduction that I'm going to show you a little bit further. So this is the SVD decomposition. So I'm trying to get the orthonormal basis for those or I'm aim to find in this matrix U the eigenfunctions, and this is the function SVD, and then I get everything. And what I get, I'm going to share. What I got after that is where this one is. Yeah, this. So by the end, I get these 4 principal component analysis, these 4, because you can get 35 principal component analysis, but if you get all those 35, you are kind of, I mean, you are not getting advantage of the solution of the problem, of the features of the problem, that you're going to have like these 4 PCAs are the most significant, or are the ones that have the highest singular values, and it means that carry the most of the variation of the data. It's gonna be carried by these 4 principal components, or these eigenfunctions. So in other words, I can build like any weather station with this as a linear combination of these 4 principal components, and I'm going to have a very good approximation to the reality without using the 35 weather station, instead of using these 4 principal components. And it's very interesting, because I got like the main features are gonna be provided by these 4 principal components. And then if I want to do like a clustering, or if I want to know some different characteristics of the data that I'm working on, I'm going to show you this figure, and I'm going to explain you what I have here. Is like I mean, I have as the x-axis is the first principal component, and the second axis is going to be the second principal component. And then I plot each weather station, and I can see kind of a clustering. We can see that these on the left of the plot, you can see that Resolute, Inuit, Churchill, and Ewick are those, I mean, are in a different cluster than all of these places in Victoria, Vancouver, Montreal, Ottawa, Winnipeg. And we can see that this clustering made in here in this plot, these places, Resolute, Iqaluit, Churchill, Inuvik, those are at the north part of the Canadian territory. and those in here are in the south of Canada. So you can see a kind of cluster, and then you can do some, in this, I mean, for this kind of problem, you knew beforehand that those places were at the north of the Canadian territory, and these were at the south. But for data sets that you don't know what's going on, you can do a clustering, and then you can make some conclusion about what can happen, and then you can make a further classification that it's going to be another kind of problem, but you have the basis with these functional principal components. And yeah, that was actually the scope that I was working on, and I had to use I used MATLAB as an environment for doing my calculation. I use coding to help me solve the problems that I have. I mean, to go looping over the 35 weather station, to compute also, MATLAB helped me to compute also the SVD decomposition without doing by hand, computing the eigenvalue. So I kind of use, and the feature of MATLAB's, for the mathematical functions of MATLAB, which are pretty awesome. And also, I use the MATLAB capabilities to plot different functions and stuff like that. And yeah, basically that. So to sum up, I mean, I had two different problems, pass from discrete data to functional data. And the techniques that I used for doing that, it was a non-parametric regression, 3 different methods, a spline method, trigonometric polynomials method, and the radial basis method. And then from to obtaining the principal components of the functional principal components of those discrete from those functional data, I use the mathematical technique that I use. It was the SVD decomposition or eigenvalue decomposition, and the computational tool that I use, it was MATLAB for coding, for obtaining the mathematical results and doing this function. That saved me heaps of work if I had to do it this, for example, in JavaScript, because yeah, it's very difficult to make multiplication of matrices in JavaScript. That's why MATLAB is so good for doing this kind of problem. So yeah, this is basically what I did for my VRES. But it's not it's not done yet, because instead of having a weather station, I have to use some I'm going to transfer this technology to work instead of weather station. I'm going to be testing this function and this technology with a sport athletes, and then I'm going to see the performance of them, because because each athlete gives you kind of a feature, and then we're gonna do the functional principal component analysis for each sportman. So after this, I have to use all this technology to do the two steps that I did, passing from discrete data to functional data for each sport athlete, or for each athlete. And then from that functional data, I'm going to perform a functional PCA, and in a group or in a set of athletes, I'm going to see what are the features that are going to help us to do some analysis on clustering and stuff like that. So yeah, basically this is it. I hope that you enjoyed listening to me about this. I thought it was going to be a little bit short up, but it took me about 20 minutes or more. So apologies for that. Okay, thanks, Simon.